Hello, friends. Welcome to Hydraulics and Hydraulic Machines class. In today's lecture, we discuss on the cavitation in hydraulic turbines. Cavitation in turbines means it's a prominent phenomena in reaction turbines. Impulse turbines, cavitation does not arise because in impulse turbine, the pressure everywhere is atmospheric pressure. So there is no question of any increase of pressure or drop in pressure. So there we don't see this phenomena at all. But in the case of reaction turbines, we found that the pressure at the entry into the turbine is high, whereas the pressure at the exit of the runner is negative. Negative in the sense that it is less than atmospheric pressure. There is a possibility that this pressure at the exit of the runner may be as less as the vacuum pressure, the the vapor pressure of the flowing fluid. The pressure at the exit of the runner may be almost same as the vapor pressure of the fluid. When the pressure at any point is brought down to vapor pressure of the flowing fluid, automatically the liquid changes into vapor bubbles. These vapor bubbles flow along the direction, and when they reach a high pressure region, they collapse. When they collapse, the surrounding fluid rushes into this place. Thereby, there will be high impact pressure at that place. For example, this collapse of the bubble takes place near the boundary, takes place on the runner blades, takes place at the entry to the draft tube. So at that point, because of the high impact pressure, cavities will be formed. As these cavities are inside, which we will not be able to observe, over a period of time, these cavities extend, and finally, the efficiency of the turbine drastically fall down. So that is why we are supposed to continuously observe that the cavitation does not take place in case of reaction turbines. Otherwise, the runner blades get damaged, the draft tube entry gets damaged, and this damage is phenomenal. You can see the photos which I have placed to you before my lecture. How the cavities are formed and eroded the material of the runner, and that type of thing leads to fall down of efficiency. So that's why how to really prevent this cavitation in case of reaction turbines. So that is the topic. There are two things here. One is Thomas cavitation factor, other one is critical cavitation factor. How to really calculate these two, and analytically, how can we say that the cavitation free turbine? So this is what today's lecture is all about. So cavitation in hydraulic turbines. Cavitation generally we observe in reaction turbines. Pelton turbines, cavitation not possible. Why not possible? Pressure is atmospheric everywhere. Whereas reaction turbines, pressure at the entry is high and at exit it is negative. If this negative pressure is equal to the vapor pressure, water, then cavitation occurs. Then what is cavitation? Formation, please note it, formation, right? This is growth and collapse. Three things should happen: formation, growth, and collapse of vapor bubbles due to reduction of pressure to vapor pressure of fluid at a point is called cavitation. So in cavitation, when cavitation occurs first, if the pressure drops to vapor pressure of the flowing fluid, cavitation occurs. How the cavitation occurs? First, the moment pressure drops to, the moment you remember, the pressure drops to vapor pressure of fluid, what will happen? Vapor bubbles formation. Vapor bubbles formation. And these vapor bubbles travels along flow. And then what will happen? They collapse when the bubbles reach a high pressure zone. Then what will happen? Surrounding fluid rushes into the collapsed bubble and apply a very high impact pressure. Due to this high impact pressure, what will happen? Cavities are formed on the surface. For example, if the bubble collapse on the runner blade, then cavities are formed on the runner blade. And what it results in? Efficiency. But remember that this spoiling of the runner blades, we will not be able to see also. That is one of the difficulties. So inside it goes on for a long time. Today maybe a small chipping on the runner blade. But tomorrow, as the time progresses, that chipping goes on increasing. Kindly see the figures which we have. See the figures posted here, posted at the beginning of this lecture. So next what? Basically, what should we do? Where actually this cavitation occurs? Cavitation occurs where in reaction turbines? Or in other words, which parts get damaged due to cavitation? Number one is runner blade, and number two is draft tube. These are the two components which will get damaged due to cavitation. So, how to really prevent this cavitation, this prevention of cavitation? There is nothing like any cure, what you call it as you can cure it. Only with the measures that you can take, it is only for prevention. There is one factor we call it as Thomas cavitation factor. Very, very important. Thomas cavitation factor. This we call it as sigma. It is defined by Thomas. How he defined? It is equal to HA minus HV minus basically HS divided by H. What is these things? Number one, what is H? The working head. That means net head acting on the turbine. And then HA means what? Atmospheric pressure head. HV means what? The vapor pressure head. This is related to the liquid. Then what is HS? HS is equal to height of turbine outlet above tail race. This is also called, some people will call it as suction pressure head, meaning is height of turbine outlet above the tail race. So using these factors, because atmospheric pressure is known to us, vapor pressure head, any water is known to us, and height of suction, that means suction pressure head, at what height we have kept it, that also we know, total working head. So knowing the above, so we can calculate sigma, knowing HA, HV, HS, H. So this is over. Then what is the other thing actually? There is one more point called as critical cavitation factor. Critical cavitation factor. This critical cavitation factor depends on specific speed. It depends on specific speed. This value for Francis turbine is equal to sigma C is equal to 0.60625 into NS divided by 380.75 whole square, where NS is the specific speed. So knowing the specific speed, we can calculate sigma C. For propeller turbine, sigma C is equal to 0.28 plus 1 by 7.5 into NS by 380.78 whole cube. But we are not interested in propeller, but for Kaplan turbine, sigma C is equal to 10% more than propeller turbine. Because propeller turbine they have given, so Kaplan turbine generally we take 10% more. So in all these two, three, the equation is for NS is known. If NS is known, sigma C is calculated. So knowing NS, calculate sigma C. So we have here two things with us. One is sigma, the other one is sigma C. Sigma is Thomas cavitation factor, and the other one is critical cavitation factor. So these two are known to us. Knowing these two, if sigma is greater than or equal to sigma C, then no cavitation. Please remember, if sigma is greater than sigma C, no cavitation. That means Thomas cavitation factor is greater than or equal to sigma C, then no cavitation. If sigma is less than sigma C, cavitation occurs. So always remember that your specific speed should be such that your always your critical cavitation factor is less than Thomas cavitation factor. So this we should remember. And here I will stop this lecture on cavitation in hydraulic turbines. And let us summarize two things and learn the important things. The first thing that all you should remember is in the case of cavitation in hydraulic turbines. Cavitation in turbines, if I say, automatically you all should know that it is in reaction turbines, whether it is Francis or Kaplan turbine. That is the first thing. Second thing is which parts can damage because of cavitation. It is runner blade or the draft tube beginning. Third, why they get damaged? Cavities are formed. Why cavities are formed? Because when the pressure is less than that means vapor pressure of the fluid, automatically vapor bubbles form. If these vapor bubbles collapse, automatically these cavities are formed. So this we should remember and then move forward. Right? With this, I will stop this lecture. Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.